I hope you guys can see my screen. Can anybody give me a thumbs up? Yeah, good, good. Okay, so yesterday we discussed about FODEM, fixed OADM. So when we discussed about FODEM, we were talking about everything being hard patched with one another and requiring of manual intervention to any kind of modification or troubleshooting purposes, right? So on the other hand, we have a dynamic system as well, which we call RODEM, reconfigurable optical add drop multiplexer. So RODEM is a process or is a technology which help us to dynamically manage wavelength in DWDM system. In RODEM, both the pass-through and the add-drop wavelengths are reconfigurable. That means the 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 availability of RODEM in your system actually help you to manage all kind of wavelength addition or drop or pass through dynamically managed. So this is very flexible. This is a very fast approach to uh, work with a network, and this is a very real-time based dynamic solution. And the main technology behind it, we call it wavelength selective switches or WSS. So WSS is the part which comes with RODEM, and this WSS basically helps RODEM to act like a dynamic manager for all the wavelengths. So with the help of wavelength selective switches, as you can understand the name, wavelength selecting switches, we can basically select wavelengths and we can switch them based on our selection. And everything is controlled by software. That's the main part. You do not need to do manual intervention. You do not need to do physical intervention. Everything will be managed by your NMS, your software. So it's life made easy. So there are several types of RODEM, like a broadcast and select RODEM, and a wavelength selective RODEM, and CDC or colorless, directionless, and contentionless. So these three types are categorized based on the output efficiency or based on the network architecture. But if you focus on the technology, if you focus on the technology, basically RODEM will be two types, broadcast and select, and wavelength selective, WSS. So these two main categories will be there. So if we talk about the categories of RODEM, you can see here in this slide, I have inserted a table which shows the difference among the three categories we just discussed: broadcast and select, wavelength selective, and CDC, colorless, directionless, contentionless. So when we say broadcast and select RODEM, we mean that it's kind of doing broadcasting. When it receives a signal, it broadcasts that signal to all the output ports. When we talk about wavelength selective RODEM, we talk about having our control over selecting a specific wavelength and forward it to a specific output. When we talk about colorless, directionless, and contentionless, here basically we mean that there is no restriction from where to where and which wavelength can travel. In case of broadcast and select, all the wavelengths which are received by the WSS will be broadcasted to all the output channels, and the output channels will actually uh, forward the wavelengths towards the next uh, connectivity or next hop. But if we talk about wavelength selective ROADM, here we can specifically choose a wavelength, but we cannot choose the direction all around. It is a bit confined in terms of direction. So when we are working with wavelength selective ROADM, we are not talking about directionless. It might be any wavelength based on our choice or based on our specification or based on the network design, but the direction will be not entirely flexible. But when we talk about CDC ROADM, in CDC ROADM, there is no restriction on wavelength, there is no restriction on direction. Any wavelength can travel from anywhere to anywhere. Even in the path, the wavelength can be changed by the ROADM itself. So that kind of ability is there in CDC ROADM. So that is what it makes a very flexible, highly efficient, robust network. At the same time, CDC ROADM network architecture are really, really costly, and it costs a fortune. When we talk about broadcast and select ROADM, that is also a bit of wastage, since you are investing money on ROADM, but you are taking the taking something which basically have lower efficiency. So for practical experience, from my practical experience, we saw that wavelength selective ROADMs are some sort of middle lane of solution, which basically gives you enough flexibility at the same time help you to reduce some cost as well. So as you can see, the comparison is there in the table, so you can go through the table whenever you want. I'm not going to read out the table. So what is the working principle of ROADM? How does it work, right? So at first there will be an input signal for the ROADM, right? A signal has to come, into the ROADM so that the ROADM can work with it, right? So there will be an input signal. This input signal, basically the multiplexed signal, which is coming from the DWDM system. Then the signal will be splitted, but not necessarily always. It depends on the type of ROADM, which type of ROADM we are using. If it is a broadcast and select ROADM, then the signal splitting will take place. If it is a wavelength selective ROADM, then the signal will not be splitted. The signal will be selected with a specific wavelength. So there's the difference in working principle for these two technologies. Next is a wavelength selection. So the WSS identifies a specific wavelength that need to be added, dropped, or routed. So as I was saying, when we talk about ROADM, we are basically talking about having uh, flexibility, having our independence to choose wavelength as per our requirement or our design. And we can do it from software. There is no manual intervention. So that is what basically make this thing great. So if we talk about the wavelength selection, as we discussed, broadcast and select, wavelength selective ROADM. These two types are there. So when we use broadcast and select ROADM, the signal, the input signal will be splitted and it will be forwarded to all the output ports. When it is a wavelength selective ROADM, then the input signal will be processed and specific wavelength will be forwarded to corresponding output ports. Next operation is adding or dropping. So for dropping of wavelength, WSS directs specific wavelengths to drop ports, which connect to local devices or systems. And these dropped signals are processed locally. For example, used for communication within a regional node. And if we want to add a new wavelengths are added from local devices as well to the add ports. The added wavelengths are combined with the remaining optical signals. So when it does the dropping of the wavelength, it picks the specific wavelength to drop port, and the drop port is connected to the client, and that port do the processing of color and gray lambda, and this is how all the traffic is delivered to client. At the same time, if we want to add a new wavelength is connected to the add port, and that wavelength is combined with the remaining optical signals to push forward. Next step is signal recombination. So as I was discussing, when a WSF recombines the remaining wavelengths and newly wavelengths, they need to be merged into one single optical signal. That is what this signal recombination means. Then we have the output signal transmission. So after making all the recombination and getting one single signal, that signal is forwarded to the output fiber for further transmission towards the next node in the network. So this is the working procedure. And most importantly, all of these can be achieved with the help of your NMS or software. It can be done without involving people. So all the operations here are software controlled, NMS controlled, and you can do everything from your NOC sitting in front of your NMS server. So that's the beauty of it. So if we summarize the workflow with an example, it will look like this. The first one is the incoming signal, which is a signal, a composed signal consisting all the wavelengths together in a single signal. Next, we have the drop operation where the ROADM drops the wavelengths. For example, lambda 1 and lambda 2 are dropped. Then we have the addition operation where we add new lambdas. For example, lambda 81 and lambda 82 are added. And then we have the pass-through operation, which is except lambda 1 and 2, which were dropped. That means from lambda 3 to lambda 80. And then we have the output signal, which consists lambda 3 to lambda 80, and the newly added lambda 81 and lambda 82. So they are recombined and they are sent towards the output signal port to go to the next destination node. So this is the work summary of ROADM. Now, if you tell me to discuss in brief about FOREM and ROADM, what are these? So if I talk from a higher granularity, so these two are basically two architecture of DWDM network design. One is designed with fixed hard patched scenario. Another one is designed with some dynamic card where the operations can be handled dynamically with the help of NMS software. So one is not flexible, another one is really, really flexible. So when we talk about flexibility, we also mean about getting higher terms of redundancy, higher terms of quality of service, and lots of other features as well. When we use ROADM, we can basically facilitate some more features into our network. And one of those features are ASON, automatically switched optical network. So when you insert ROADM or when you use ROADM in DWDM network, that means you have dynamic control over wavelength. You have dynamic control over the direction of the wavelength. So if you can manage the wavelength and its direction dynamically, and if you can do some automation to do it for you so that the machine can take care of itself, then you can understand the level of certainty or the level of comfort or robustness your network is going to show, right? So keeping that in mind, the automatically switched optical network or the idea of ATON came in picture. It is under the G.8080 recommendation by ITOT. So if you search internet with this recommendation, you will be able to know more written details or documentations on ASON. But here I'm just going to clear the concept, or I'm just going to discuss the concept or idea behind ASON. So I'm just going to make you understand what ASON is all about. So if we talk about the key features of ASON, so dynamic connection management, intelligent control plane, service awareness, scalability, resilience, and restoration. So when we talked about optical line protection or schemes like that, we learned about redundancy, right? We learned about protection. So if one path goes down, then the other path will be able to carry the traffic. When we talk about ASON, we have another term which we call restoration. Here we are giving our traffic a third chance to survive. So what is happening? We saw for optical redundancy, there is only one way to select a path, and that way involves having only two options. primary and secondary, right? When we discussed OLP or optical line protection, we saw that there is only two paths, primary path and secondary path, right? So if one path goes down, another one will take the traffic. That is how it has been like this in OLP. But when you use ASON, you can have a third path and you can educate your system to provision the third path when the first path goes down. So what happens in ASON, the traffic have primary path and the secondary path provisioned and third path in a queue, not provisioned. When the primary path goes down, the traffic is shifted to the secondary path since secondary path was already provisioned. At the same time, the system starts provisioning the third path. And after completing the provision, it established that third path as current first path. Now, the traffic is again protected with two provision paths. So, do you understand what I'm trying to say? If anybody has any query on ASON, please let me know. Okay, all good. I didn't see query. Okay, there is nothing in the chat. I can see, yes, Satish.
You have said that 1 plus 1 plus R, third redundancy, right?
Restoration, not redundancy.
Yes, restoration path. So, in if optical path is only two available, so how third will be logically you can provide?
So if there is no third physical path, ASON will not work.
Yes.
As I was saying, it can only be achieved when you have a third physical path. If you do not
Okay.
have a physical path, so what is happening
And,
in
and one more question. If I have three, four, or five physical path available, so may I configure all five in the redundant mode?
not redundant mode, you can queue the paths as a restoration mode. So whenever,
Restoration. Yes, exactly.
yes, so whenever one of the path goes down, so at any given time there will be two provision paths. Okay, at any given time there will be two provision paths so that in case of a failure the traffic can be switched within 50 milliseconds. When one path goes down, the third path will be taken by the system and will be provisioned. Again, there is two provision paths. Suppose the second path has went down, the system will pick the fourth path and it will provision. Again, the traffic is now protected with two paths. See, I hope you understand what I'm trying to say.
Yes. Just for further clarification that each logical path must be defined for this. Am I correct?
It's a it's a yes and no answer. So yes, the logical path must be defined, but you cannot basically configure the path at the same time because the configuration has to be unique throughout the whole path. And
For the particular OADM location, I need particular 2 or 5 lambda. So how it will be get defined?
sorry, can you ask again for a particular location?
For the particular OADM location, which is in between the node somewhere, and at that location, I need only 2 lambda drop and 2 lambda add.
Yeah.
So how it will get defined for the five different logical path?
Okay. Suppose you have a location which has, okay, I think I need to go to the screen and draw. Let me change the video. Sure. Can you see the screen?
Presentation screen is visible, not other one, whiteboard.
The video, can you look into my video? You should be able to see the screen.
Just may switch on video.
Um,
On video also only screen is visible.
Yeah,
Presentation screen.
yeah. Okay, okay, exactly. So that is what I actually wanted to show. Anyway,
Okay, now visible.
so suppose you have a location here. Just so suppose you have one location here. Okay. From this location, you have 5 pair of fibers. And they are all connected to your network house. And at the other end of the cloud, there is a destination which has maybe 4 paths. Okay. So we talked about OLP, optical line protection. So what happens in OLP? Light comes in, it's splitted into two, and it goes via two physical paths. At the receiving end, there is a switch. That switch selects one of the link. When that link is cut down, the switch fall back to the second path. This is how the receiver have the protected traffic. Is that clear?
Yes, for two path it's clear.
Okay. The same OLP concept is applied here. So the signal from OTU comes here and splitted into two paths. And these two paths are provisioned to carry the wavelength. That wavelength is suppose lambda 1. This is lambda 1. So this is the working path. This is the protection path. Suppose these two paths are completely unique paths. They do not touch each other by any means throughout the whole network. And then these other paths, suppose they are having some common portion. not completely entirely unique. You get my point, what I'm trying to say?
Yes.
So when a lambda is provisioned in a path, that lambda cannot be repeated. If you take a look in this path has a common portion with the provision protection path, right? So if
Yes.
you want to use this path has to be unconfigured, right? At the same time, if you want to configure this path has to be unconfigured, right?
So you mean each path must be configured, not pre-configured.
Each path must be pre-selected, not configured. You
Pre-selected. Okay.
Yes, you can only configure the working path and the production path. Suppose the working path has gone down. Now look at the scenario. The traffic will be switched within 50 milliseconds to the production path, right? This is the first thing. Second thing, there is no working path. The system has some selection of path which it can provision now as the working path. The system will take a look. The system will look at this link. It will see that there is a common portion with the production path. It cannot create the link using this fiber. So the system again will take a look on the other available option, which is this fiber. This fiber has the unique direction where it doesn't touch in any way with the protection fiber. So the system will take this path and the system will configure this path and make it the working path, and it will be channelized. It will channelize the traffic via this path. Does it make sense to you?
Okay. Now, what is a practical challenge once I have faced is that whenever the first path is out of service or breakdown, on second path only all of the lambda get diverted, but only one or two lambda services which was not restored on secondary path. So what could be the reason?
So it can be it can be a whole set of dynamic reasons or various reasons can be there. First of all, there might be some portion in the second path which already has that lambda provision in it. So if the system is trying to reconfigure the lambda in the second in the tertiary path, actually not secondary. So if the system is trying to reconfigure the lambda in the tertiary path and they cannot be configured, that means there might be some portion in the network in that path where the lambda is already existing, or there might be the distance of the lambda which it is traveling is not being supported due to poor OSNR. That might also be a reason. See,
Yeah, that optical power was on threshold, so it made possible.
I'm talking about OSNR. These two are two different things. We already discussed the difference between optical power and OSNR. Optical power, you can have exact, perfect, satisfying level of optical power, yet a very poor OSNR. Okay, so optical power might be good, but OSNR might be very bad. That might be one of the reasons why this lambda couldn't be created. That could be the second reason. Third reason, sometimes the WSS cards got hanged because these WSS cards, they are doing lots of filtering, wavelength selection and all those things within a very tiny card. So sometimes, in my experience, what I have seen, I had to reboot the WSS card for certain direction for specific lambda to be rerouted. So if the first two reasons are not there, like if the lambda is not repeated, like if the OSNL level is still good on the third path, should be good on the third path, then you need to look at the third probable call, which is the hung of uh, the freezing state of WSS. You might need to reboot your WSS card to provision the lambda there. And you can understand that by looking at the log of your WSS card. So you can if you have access to the logs of your cards, you will see that your WSS card is frozen and it will keep failing the same procedure again and again and trying again and again. Or it might not receive any signal at all, or it might not sense the wavelength at all. So this kind of ambiguous logs will be there behind the card. So you need to talk to your vendor if you do not have access to the logs of the cards. Again, for some vendors, the logs are kept secret. For some vendors, the logs are kept uh, symbolic so that only the engineers from their own organization can understand. So lots of dependencies are there. So I would recommend you to work closely with your with your vendor, and only then you will be able to actually find out what has happened. I hope that answers your question, Satish.
Yes, thank you.
You
So,
moving?
may I have, uh, can I question another?
Yes, please.
Yeah. So, thank you. So in this case, if there is a constraint in the path, okay, so it will not restoration within the 50 milliseconds. So, according to the practical experience, sometimes if there is a constraint, it takes sometimes second level also. So, if the preset path is already occupied, okay, so if still other path is free, so system can automatically provision the next lambda
So,
for optical lesson for optical lesson.
yes, I got your question. So what you're trying to say that in some cases the restoration takes time, right? And
Right,
what will happen if there is a second card on the protection fiber before the restoration kicks in, right?
right.
Yeah. So 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 see, the thing is that let me switch the video. Yeah. Okay. Okay. The thing is that when there is it depends on the size of your network, on the number of the WSS and amplifiers in your network, that what is the required time to provision a path from end to end, from one point to another by your system. In a large network, it should take 3 to 5 uh, minutes if the provision needs to be done from the beginning. In some vendors, you can pre-select and you can use those selection as a preset. So when you use a preset, the system does few works ahead and only the cross connections are left. So in those cases, it may take a lot less time, but still, depending on the size of your network, it should be 2 to 3 2 to 3 minutes at least. So when the system is doing restoration and there is a first card and a second card, at that moment you do not actually have any provision path, and that few minutes you will face outage. That's for sure. You cannot escape it as much as you want. That is a given. You cannot escape it. To fight this scenario, there are some scheme of configuration in Athon where different vendor name them differently. I'm not going to use the name or terms here. In those schemes, vendor try to incorporate more WSS, more layers of WSS, and try to make sure that there will always be two provisioned paths, one behind another. So in those kind of scenarios, it is only possible to make sure that there will not be any outages. But those solutions are really, really costly. Vendors are gonna actually come up with a solution which will involve a lot of WSS, which will involve uh, high grade of WSS, something like that, which we discussed earlier, like CDC. In those cases, there will not be any dependency on any direction on any wavelength. But if there is no physical path at all at any given time or any given point, then actually you have nothing to do. You at least need one physical path to do your configuration. So if there is no physical path at all, then there will be a outage of your traffic. I hope that answer your question, Saleh Ahmed.
Thank you. Thank you.
Thank you. So moving forward, uh, in my experience, what I have seen in my previous experience, what I have seen when in our previous network where I used to work, in previous network there was around uh, 40 or 50 boxes of same vendor for one network. We had a couple of segmentation of networks. So for one of the network, it has 40 or 50 boxes from the same vendor and one single design. In that network, it took around 3 minutes to provision a lambda from one point to another. And this is the average timing, considering the lambda has to cover a total distance of around 3 to 400 kilometers of length. In this distance, the lambda had to pass through multiple nodes, multiple amplifiers, multiple WSS. So the system has to do all these steps of provisioning. So from start of the restoration task to the end of the restoration task, the average timing was around 3 to 4 minutes. So in that 3 to 4 minute of timing, the traffic would be at risk. The traffic would be live only on one fiber. If there is a second card in that 3 to 4 minutes, then we have experienced outages for a couple of times. And that means you are just being unlucky because you will choose the two most unique paths to be your working and protection. And you would want to have those paths to be dynamic in several ways and to be different from each other in several ways. So it should not be like this, that you are having primary cut and secondary cut within 3 to 4 minutes. But if it happens like that, that means you are either unlucky or the uniqueness of those two paths are not that diverse. That means somewhere down the road, the paths are not that distant from each other. They are being affected by same kind of surrounding or environmental effect, like road expansion or fire or natural disaster, whatever it is. So I hope that answers your question, Sarah.
Yes. So in this kind of case for the mission critical services, so we can use electrical as well, right?
Yeah, I'm going to discuss this in coming slides. So just stay with me so that I can continue the discussion.
And for the optical action, we can manually switch to the protection or the restoration for I mean the plan in the plant maintenance window and clear the constraints. Okay, before the restoration. So I think it helped to restore faster. So we did like this. Okay, this is like just our experience sharing with
I didn't get your second point.
you. So we have planned activity for the optical lesson. Okay. So switch manually to the secondary path or the restoration path. I mean the preset and test. So if failed, then clear the path of the constraints. So after constraints, then when it is need to automatically switch, it switch better. I mean less millisecond.
So the scheme you are talking about belongs to one specific vendor. So as I was saying from the beginning, I am trying to keep this as much generic as possible.
Yes.
So the scheme you are mentioning belongs to one specific vendor. It's not applicable to all the other vendors. Okay. Preset,
Okay.
the preset option which you are saying, in the preset option, the system does the neighbor discovery, does the path discovery protocol activities beforehand, and keep that in its database, so that when the time of restoration appears, it just does the cross connect based on that database. But other systems, when the time of restoration comes, they do the neighbor inventory discovery, they do the OSPF, they do the GMPLS, they do the traffic engineering, everything, and then they provision the path. So are you getting what I'm trying to say?
Yeah. I got your point.
So yeah, there are some vendors who have some features which can help you to get a faster solution. There are some different technology as well which can help you to get a good quality of service, but of course, the cost is really, really high. I'm coming to that. I'll discuss. So
Okay, thank you. Please.
yeah, so okay. So as I was saying, when we talk about ASON, we basically trying to say that uh, having a third path or n number of paths for our traffic to be restored, not protected. It is there to restore the path. So when we talk about protection, we mean there is a working path, there is a protection path. When we talk about protection, we mean there is a working path, there is a protection path. When we talk about restoration, or when we talk about ASON, we basically mean there will be couple of other available paths to be used after the first two goes down one by one. That is what it means in simple words. Okay. So if you are getting what I'm trying to say, that is the concept of ASON. It has dynamic connection management. What it means that automatically establishes, manages, and releases optical connections without manual intervention. It has intelligent control plan, which means it has a control plan which make all the decisions for all the routings, all the planning of traffic engineering and everything. It has service awareness. That means you can basically prioritize your service based on bandwidth or latency or some other factor, jitter and some other factor. It has a feature of scalability. It supports large and complex networks with dynamic traffic demands, and it has the resiliency and restoration feature we just discussed. So if you take a look here, this is the diagram which basically shows you the concept of ASON. In ASON, we have a management plan. In ASON, we have a control plan, and we have a transport plan. The management plan is there to take care of the management of the network. The control plan is there to run all the routing protocols for the network and making decisions for the traffic, which way to where, which wavelength to where, all those things. And the transport plan is there to carry the data, carry the packets, or carry the traffic, carry the frames from one place to another. So the transport layer is doing only the transportation. The control layer is the brain, it's thinking, and the management layer is doing all kind of administrative management related work. So this is the basic structure of ASA. And this is what we discussed. So in the control plane, there are several protocols. There is GMPLS, there is OSPF-TE, there is RSVP-TE. So with the help of MPLS and RSVP, the system does the end-to-end tunneling and reserves the path, plan the bandwidth or traffic engineering, and with the help of OSPF, the system does the uh, discovery of neighbors, nodes, or other inventory management things. So those things are controlled by this control plane with the help of this protocol. What are the working protocols? Connection setup. So a user can request a connection with specific requirements like the quality of service or the amount of bandwidth the user needs. The control plane based on that request can automatically find an optical path through the network, and the control plane can set up the connection from end to end based on that request. While doing that, the control plane also allocate bandwidth and optical channels, and these assignments are done completely dynamically. There is no manual intervention. The decisions are taken by the system. Then the routing, it means the ASON uses the intelligent algorithms to calculate the best route for optical signals based on factors like available bandwidth, signal quality, distance, etc. Then traffic engineering, it optimizes network resource usage by distributing traffic evenly and avoiding congestion. And last but not least, dynamic restoration. In case of a failure, for example, 5-card, ASON automatically reroute traffic along alternative paths within milliseconds. And this statement is not always true. For optical ASON, in some cases, it takes time. Okay. Okay, so these are the things I was just discussing moving forward, advantages, okay, challenges. We have some challenges with SN network. It is a complex set of network. You have to design the network really carefully so that there is a very low amount of overlap in fiber paths. We call them SRLG, shared risk link group. So you have to make sure that fibers are unique and in different paths as much as possible to get the actual flavor of ASON. The more diverse paths are incorporated into the network, you will feel that ASON is serving you with most amount of efficiency, and your traffic is enjoying uptime you anticipated uh, to have. And there is a cost issue with ASON network because this is a costly technology, and on top of it, if you take electrical ASON, so is there? Do I have the discussion on electrical? Okay, I have it on the last slide. Okay, so ASON can be two types. It can be optical and it can be electrical. In case of optical ASON, we use the optical infrastructure and we play with wavelengths from one place to another. But in case of electrical ASON, we use the wavelength structure and we play with electrical cross connect of the traffic with the wavelengths on electrical boards. So one thing, the in optical ASON, all the activities are involved with doing optical provisioning. In electrical ASON, all the activities are involved with handling electrical cross connects in cross connect board. So these are the two categories. These are the two different ASON technology we have. For electrical ASON, you need to have a lot of OTU cards, which are expensive. For optical ASON, the number of OTU cards drastically reduces, and it becomes a much more cheaper option than electrical ASON. But the dilemma is what we just discussed. When we have the protection scheme in optics, there can only be two provision paths at any given time. The rest of the path, you can either have a preset, you can either have a standby option. In some vendors, they call it in different name, or in some vendors, it's just there and they just start looking for it after getting a card in the network. So this is how it works. So as I was discussing, the cost ASON itself is a costly technology. Moreover, electrical ASON is way more costly compared to optical ASON. Interoperability has always been an issue in DWDM, not only in ASON, but also in any case of DWDM. Scalability concern. So high dynamic traffic patterns in very large networks can pose scalability challenges as well. Applications, carrier network, enterprise, data center, disaster recovery, uh, all the major traffic consumption hubs, nodes, areas, service categories which have long distance to cover with high amount of bandwidth and which needs high amount of reliability for the availability of the bandwidth. So those cases are most appropriate to deploy ASONs. Okay, so this is the difference between a traditional optical network and ASON. The connection setup is automatic in ASON, routing is dynamic, restoration is fast and automated, traffic engineering is advanced and dynamic, and flexibility is really high in ASON. as I was discussing, electrical action and optical action. So the difference between these two are plotted in this table. I'm not going to read out the table. I only discussed the highlight with you already. So what happens in electrical action, we basically rely on the cross connects of the electrical board. And in optical action, we basically rely on the wavelength and physical path and optics of the DWDM infrastructure. So that's all in this slide. So please let me know if you have any query. There is nothing on the chat. I don't see any query, so I'm going to stop this one here, and I'm going to start our next discussion, which is optical power calculation. You guys can see, right?
Yes. Yes.
So now we will talk about the calculation of optical power in DWDM network. Previously, I said that you need to understand how the calculation is done, but you do not need to do the calculation on paper with pen because your system is there to do it for yourself. So your system will help you, vendor softwares will help you. You do not need to worry about all those calculations, but you need to understand how the calculations are coming into picture. So that is what we're going to discuss here, and that is what we're going to understand here. Okay. So basic concept, the relation between milliwatt, dBm, and dB. So milliwatt is the unit of optical power. Also, dBm is the unit of optical power. And when we are mentioning dB, that means this is the unit of gain or attenuation of optical power. So this is the difference between two points, right? So as you can see in the slide, so the milliwatt and dBm, they are the absolute value for optical power. So 0 dBm means 1 milliwatt, 10 dBm means 10 milliwatt, 20 dBm means 100 milliwatt, 20 dBm minus 10 dB is equals to 10 dBm, right? So these are some things, or these are some facts to be considered. So I'm subtracting a difference from a unit, and that gives me the unit. So that is how it is done. So you can ask, how am I saying that 0 dBm is 1 milliwatt and 10 dBm is 10 milliwatt, right? Yes, please.
Sir, this 20 dBm minus 10 dB equal to 10 dBm. That you can please explain.
Yeah, so 20 dBm and 10 dB. So when we talk about dBm, this is the unit of optical power. And when we talk about the dB, this is the unit of gain. This is the gain or attenuation. So, suppose you are having an optical power of 20 dBm, right? Now, this is the power or strength of the light you are having in that fiber, right? Now, if there is a loss or gain in the path of 10 dB, so that 10 dB is not the unit of optical power, right? That is something which is actually aiding or obstructing the power, right? So if it is an attenuation, then it will be a minus figure. If it is a gain, then it will be a positive figure, right? So here, suppose the optical power was 20 dBm and the gain or attenuation was 10 dB. And that gives you the result 10 dBm. Whenever we are talking about dB, decibel, that means we are only talking about something which is coming from 10 base log. Are you getting my point?
Yes, sir.
So whenever we are talking about gain, whenever we are talking about attenuation, this is something which comes with a 10 base log unit, nothing else. But whenever we are talking about power, there is a M at the end of the decibel, right? That means there is something along with the 10 base log figure. You will understand these things in later slides when I will explain the relation between them. Just stay with me, okay? So if you take a look here, so what is the relation between milliwatt and a dBm? So it should be like this. The power in milliwatts is equal to 1 milliwatt times 10 raised by the power in decibel milliwatts, right? Which is dBm divided by 10. So P milliwatt equals to 1 milliwatt times 10 P dBm divided by 10, right? So in this formula, using this formula, you will see that 1 milliwatt equals 0 dBm and 1 watt equals 1000 milliwatt or 30 dBm, right? So it's all based on the calculation. When we work with the optical power itself, the unit is milliwatt, and that same milliwatt becomes dBm when we convert it in a 10 base log format, okay? So these are the two variations of units for optical power. But when we talk about the gain or when we talk about attenuation, so that means that's the so gain of 10 dB. So an amplifier is providing a gain of 10 dB. That means the difference between output power and input power will be 10 dB. When we talk about an attenuator possessing a loss of 7 dB, that means the difference between input power and the output power is 7 dB. So for gain or for loss, we are basically talking about difference. When we put difference in log format, 10 base log format, that will become a division for the formula of log. So pure subtraction means division in 10 base log. So when we go for the division, the units for both the fields are nullified. So only the difference remains, which comes as dB from using 10 base log. That's it. I hope that answers your query.
Yes, sir.
Yeah, okay. So as I was saying, I know these are a little bit hard because we have studied log in our early days in school or college, and we hardly use them in our real practical life. But these are the basics, so I'm trying to share or I'm trying to make you understand the basics. So just try to stay with me and move forward. So how to convert milliwatt to dBm? So the formula looks like this. So power in dBm equals 10 into log 10 base power in milliwatt divided by 1 milliwatt. At the same time, you can convert dBm to milliwatt with the formula power in milliwatt equals to 1 milliwatt times 10 power in dBm divided by 10. So using these two formula, you can convert dBm to milliwatt and milliwatt to dBm. Okay. Again, we are coming back to this picture. So we have already discussed this. So here, as you can see, P1, P2, two channels, two wavelengths, and the number of wavelength is 2 here in this diagram. The total output power is P total. So P total equals P single dBm plus 10 base log n. Here it is only written dB. See, because whenever we are working with log, and if there is a ratio, if there is a subtraction in the common field, then the units are nullified and only dB remains here. So this is how it is calculated. So we will be using this formula again and again throughout the whole slide. So P total dBm equals to P single plus 10 base log number of wavelengths we have in the system. Okay. So this system might be capable of carrying 80 lambda, but we are using only 2. So we have the formula like this. We will use n equals to 2 here in this case, in this scenario. Okay. Moving forward, noise. We talked about OSNR, and in OSNR, we talked about noise. So as we discussed, the majority, yes, Mr. Kamal.
Sir, in the previous slide, please go back. The last formula base of log is what, 2 or 10?
10 base log. So the base is 10 base log, but the number after the log is 2.
Okay, so base is 2.
No, it's 10. When we work with log, the base is 10.
Okay. Right.
So as I was discussing, when we were talking about OSNR, we discussed about noise. And we said that the majority of noise comes from amplifiers. So when we have EDFA or Raman, they are basically contributing to most of the noises in your system. And each amplifier or each Raman, EDFA or Raman or whatever the amplifier is, vendor has their ASE noise or amplified spontaneous emission noise documented in their product sheet for those cards already. So whenever you are using an amplifier in your network, try to take a look at the data sheet of that card. You will understand what amount of noise that card is going to introduce in your network. Okay. So there is a formula to find out noise. ASE noise power equals minus 58 plus noise figure. Don't ask how that minus 58 that has come. It's a long math. And I also don't know in details about that math particularly. I just know about this formula, and I'm sharing that formula with you guys. Okay. Anyway, so this amplified spontaneous emission noise, it can basically, if not treated correctly or properly, it can basically harm your network. The impacts are very, the impact involve reduction of signal to noise ratio or OSNR, bit error rate, channel interference, and cascaded amplification effect. So sometimes we need to use multiple amplifier systems one after another. So in those cases, ASE noise accumulates as the signal passes through multiple amplifiers. What can be the mitigation technique? So within the mitigation technique, we have optimizing amplifier gain. So we would try to use the gain which is at most necessary, not more than that in the system. We will try to use optical filters. We will try to lower the cascading of amplifier gains in the system. And Raman amplifier also produce a lot less noise compared to EDFA. Though it is written as a mitigation technique, that does not mean you can replace EDFA in your system right now on the go with a Raman amplifier. That is not the case. But it is written in the mitigation technique as a point that Raman introduces a lot less ASC noise compared to EDFA. Okay, moving forward, there is a concept called insertion loss. Whenever you insert the signal from a physical media to a physical media, if a certain loss will occur. This loss is called insertion loss. As you can see, this is the difference between input and output. The unit will be in dB because it's a difference. And if you keep working the math, go to the log, it will create a division in the log form and the units will be nullified and the only unit will remain is dB, which comes from the logarithm. So insertion loss is a real factor and it appears whenever there is a connection. So in DWDM system, if you take a look at the chassis, you will see a lot of hard patch and a lot of connections are there. So one card to another, one port to another, one interface to ODF. So lots of hard patch, lots of connectors, lots of cards, one after another, and they all are connected from external side, patch with each other with patch cards. So each connection has an insertion loss. So that loss will be calculated like this. So the power in minus the power out. The difference is called insertion loss. So if we take a look at the characteristics of optical amplifier, since we are talking about loss, we also need to understand amplifiers. So if we take a look at the characteristics of optical amplifiers, so far we have discussed about the technology behind amplifiers, about the types of amplifiers. Now we are talking about the operation of amplifiers. So when we talk about the operation or characteristics of optical amplifier, we have few terms like nominal input power, like nominal output power, or maximum output power of a single wavelength, something like that. If you take a look at the picture, you will see P in, which is marked as a circular one, which is basically nominal input power. So the power of the wavelengths which it has while it gets into an optical amplifier, that is what we call nominal input power, which is required, to attain an appropriate level of gain and maintain appropriate OSNR throughout the whole network. That is what we call nominal input power. And the power which a wavelength has when entering an optical amplifier is the simple input power of the wavelength. When we call nominal, that means this is the required power. The nominal output power means the power which is calculated based on considering the gain factor of the amplifier. So that is the nominal output power, which basically also sometimes give you the maximum output power as well. So as you can see, the formula of gain equals P out dBm minus P in dBm. Again, since we are seeing a difference in optical power in log, the dBm will be nullified and only dB will remain. That is why we term gain as a dB unit, not dBm. So gain, the formula of gain equals power out dBm minus power in dBm. So what does it mean? So as you can see, the gain of single wavelength is the same as that of multi-wavelength for amplifier. So if a single wavelength enters into a optical amplifier and gets out of an optical amplifier, the gain is the gain on that single wavelength is equal to the is equal to multiple number of wavelengths entering and exiting the optical amplifier. So it is all the same if there are one signal or if wavelength or if there are multiple wavelengths. So both cases, the gain will be equal or same. Now we need to understand how this works. Okay. So as you can see here, there is the in, there is the out, and in between in and out, there is an optical amplifier. So suppose you have picked an optical amplifier and the datasheet says the gain of the optical amplifier is 20 to 31 dB. Okay. So that means the maximum output power is supposed to be 20 dBm. Suppose the system is a 40 channel system, we will find out the nominal input per channel. So what is the input we require per channel to make sure that the maximum output will be 20 dBm and the gain of the optical amplifier will be in between 20 to 31 dBm. Okay. So when we calculate this kind of scenario, we try to use the lower threshold of the gain so that we can go upwards if required later. Okay. So we will do the calculation considering the gain from the optical amplifier is 20, the lower threshold. Okay. So if you take a look at the slide, the nominal output, that means actually the maximum output, which is we are looking at 20 dBm, right? So we are trying to get an output of 20 dBm. So if we put this into the formula, we will find that P total out equals P single out plus 10 base log number of channels. So this is a 40 channel system, right? So it will be 10 base log 40. P out, what we are expecting is 20 dBm. So the formula will look like this: 20 dBm equals P single plus 16. That gives us P single out equals 4 dBm, right? That means each wavelength should have individual output power of 4 dBm. Now, what do we know? We know gain equals output minus input. We know about the gain, which is 20 dB. We know about the output, which is 4 dB. So, putting these two figures, we can find out that the input of each wavelength should be minus 16 dBm. So that is how we calculate the input power of each wavelength or each lambda. The good news is your system will do it for you. You don't have to bother the calculation. So try to understand what is happening here, but don't get worried with all these calculations. That is what I'm trying to say. Okay. Yes, Mr. Kamal.
So when you're saying gain is 20 to 31 dB, so that corresponds to maximum output power 20 dBm. This part is, can you explain?
So the booster or the optical amplifier itself can actually amplify the power 20 to 31 units. Okay. So take a look, it's dB, not dBm. And you are again comparing dB with dBm. The output power is dBm. This is the power of the optic. This is the power of the wavelength. And the gain is about the unit, how much unit it can pump, it can increase.
Sir, what I mean to say, 20 dB gain corresponds to okay 20 dBm, or 31 dB is also correspond to 20 dB.
No. So the thing is that the amplifier has a range of boosting the signal starting from 20 dB up to 31 dB.
Okay.
So whatever the value you select, it will create an impact on the power level of the optical on the signal on the power level of the signal, and it will make the output different. Okay. So now we have a required output power. What do we need? We know that because the next connectivity will only allow that single value. Maybe the next connectivity needs to have 20 dBm as input power. Okay. So power from the optical amplifier should be 20 dB, 20 dBm. You're getting my point? No. Okay. Just stay with me. We will work with some exercise, and I think at that time your confusion will be clear. But for now, try to understand that I have been telling this again and again. For now, try to understand there is a clear difference between gain attenuation and optical power. So gain and attenuation are the difference between two optical power, and optical power itself is another concept.
Sir, that point is clear, sir. Only my question is, gain is varying from 20 to 31 dB.
It can
So
vary
definitely, sir.
one specific value which you want.
So my question is like, if gain is 20 dB, still output power will be 20 dBm. If gain is 31 dB, still output power will be 20 dBm.
No, if the gain is 20 dB, here in this case, in this scenario, the gain is 20 dB and the output power is considered as 20 dB. But in other case, in other scenario, it will be different. Also, if you use 31 dB as a gain in this example as well, the result will be different.
Okay.
So
Got it.
So what is happening? Suppose you have suppose you have a stick like this, okay, or suppose you have a stick like this, okay, okay. So I have a sticker like this, okay. So this is the length of the sticker. This is the length of the screen size, right? So I can either put here or here or here or here. So if I put the sticker here, the total length will be large, right? If I put the sticker here, it will be larger than the original, but it's still not larger than the previous one. If I put the sticker here, so it will be in the same size, right? It depends where am I putting the sticker. So if I use the gain in a negative value of inputs, the positive value outcome will be adjusted accordingly, right? So 0 plus 20 equals to 20, but minus 10 plus 20 will give you plus 10 only. Okay,
Thank you.
so we need a maximum output power of 20 dB. We need a maximum output power of 20 dBm to make sure that to get 20 dBm of maximum output power, we are using the lowest amount of gain of optical amplifier so that we have gain in hand to be used in future. But suppose we are using the highest amount of gain. Suppose we are using 31 dB, okay, which is not ideal, which is not recommended, which is not practical. But for the sake of discussion, suppose we are using the gain as 31 dB. So what will happen if you take a look in this calculation, the input power will be 4 dBm minus 31 dBm. That will give you 20 minus 27 dBm. You understand, Mr. Kawal?
Thank
So when you change the gain and use the higher level of gain, the input will be going further negative zone or further away from the intended value. So this is what all about, just balancing the power based on the required situation. There are some other losses, basically different categories or varieties of insertion loss. There are insertion loss of different active cards like multiplex or demultiplex unit, insertion loss of DCM, insertion loss of WSS or RODOM unit. There are insertion loss of fiber interfacing unit, and also we have OTU launch power to consider as well. So when we talk about power, when we talk about losses, we have to make sure that we are considering all the factors that are available to us. These are the prime basic focus of different powers or losses in DWDM system. So it is optical, it is, as I was saying, it is balancing the optical power. So if you take a look here, as you can see in the diagram, this is a pretty straightforward generic diagram of a DWDM system where there is optical tributary card, there is optical multiplexer, there is optical line amplifier, there is optical booster, optical preamplifier, optical demultiplexer, then again optical tributary cards, and the outputs are there, right? So if you take a look, two channels are in this example. I think it is kept an N, but if you consider that there are only two tributary cards with two tributary ports, so there will be two channels, right? So it depends on the number of tributary cards. So you can have a lot of numbers of tributary cards or OTU cards as well. So based on that, the N will be defined. So if you have 10 cards or 10 channels or 10 lambdas, so the number of N will be 10. And it is advisable that the power of two wavelengths, right? So the difference, so the difference between any two wavelengths, the optical power, it is recommended to keep it under 4 dB. Some vendors are more aggressive. They will tell you to keep it 3 dB. They will tell you to keep it. Some will tell you to keep it 2 dB. but in practical 3 to 4 dB is okay. So as I was saying, the optical power difference between two wavelengths should not be greater than 4 dB. So the lesser the difference, the better the result. So that is what we need to understand. So as you can see here in this diagram, when a channel is transmitted, it passes through a lot of segments. It passes through optical amplifiers, it passes through multiplexers, demultiplexers, it passes through different segments of the network, fiber units, ODFs, and all those things. So it passes through a lot of losses at different points, at a lot of places, right? So the optical power of each channel becomes different considering different connectivity model or different patch cords, different fiber path, etc., etc. So when you are working with a set of wavelengths from a set within a set of space, specific source to specific destination, it is recommended that for that set of channels or wavelengths, the optical power of those wavelengths should not differ with each other more than 4 dB in range. So that is what it is recommended, because if you can do that, the performance of the spectrum, overall spectrum, will be very good, and your clients will have uninterrupted clean traffic as much as possible. And also, if you take a look at the transmit power of the OTU cards, it basically varies from card to card, type to type, vendor to vendor, but in generally it is about -2, -1, -3, or something like that, the transmit power of the OTU or TX cards. So, okay. So as you can see, there are some variations of calculations, because if you take a look at the type of mux and demux unit, there is two types of mux, AWG and coupler type. So array wave guide multiplexer and coupler type multiplexer. So the AWG multiplexer are having 7 dB of insertion loss. For coupler type, optical multiplexers are having 15 dB of insertion loss. So when a signal just enters the multiplexer, it loses 7 dB of its power right at that contact. So you can understand how the powers need to be minimized and balanced throughout the whole path. At the same time, if you are working with a demultiplexer, it is again for optical demultiplexer made with AWZ, the insertion loss is 7 dB, and for grading type, the insertion loss is 15 dB. That means there are two types of mux and there are two types of demux. For AWZ mux and demux, the insertion loss is 7 dB, and for grading type demux and mux, the insertion loss is 15 dB. So we basically try to use the AWZ one, which have the lowest amount of insertion loss, and that uh, type of mux and demux basically helps us to keep the loss within range in our calculation. So what are the formula for finding out the power? So optical mux output power equals optical mux output power equals log 10 PM minus insertion loss. So all the notations are described here in the slide. As you can see, PM means the total multiplex input power. Pi means optical power of each wavelength, and n equals the number of input wavelength. Okay, so these are the factors we have here. This is the formula we have here based on this scenario. And we are talking about this because we are going to see an example with powers, and we are going to calculate the value in upcoming slides. Before doing that, we need to understand the segments where the losses or the powers we are calculating and how we are calculating. Yes, Mr. Satish, yes.
Earlier, you have said that insertion losses occur from the passive devices, right? Like a passcode.
Not necessary. I said whenever there is a connection, whenever there is a patching, when you take a look at your DWDM box, you will see from external view, each card is patched with another card with external patch port from
So,
to active port. Some are connected from passive port to active port. So whenever there is a connectivity, there is a point of contact, insertion loss occurs. That is what I say.
so that insertion loss is addition to this 7 dB from the AWG mux.
So, so for AWG marks, the insertion loss itself for only this marks is 7 dB. Whenever it is getting connected to the OBA, there will be an insertion loss. Whenever it is getting connected to fiber interfacing unit, there will be another insertion loss. And these losses vary from point to point, card to card, etc. Okay, so this is the concept why this kind of things happen. So whenever you are connecting from one point to another, there are connectors, right? At two end of the connection, there are connectors, and there are interfaces at the both end, right? SFP. So whenever you are patching or you're connecting, the point of contact is not 100% smooth. So that give you some loss, or that generates some loss. For AWG marks, DMarks, or for grading type marks, DMarks, the amount of loss, or even for WSS, the amount of loss is really high. Why? Because when the signal enters into one of these, the internal view of these cards or these devices involve lot of components where the signal goes in and goes out, goes in and goes out. So a lot of splitting, filters, and prism scenarios, couplers, lots of things inside one single card. So that is how insertion loss for these cards like WSS or multiplexer or demultiplexer are at such a great extent, like 7, 15, 10, or 8 dB or something like that. But for normal cards like fiber interfacing unit or like other OLP or something like that, it is only about the loss of point of contact. But in both the cases, we term them as insertion loss. I hope that answered your question, Satish.
Yes, clear.
Thank you. So just take a note at this diagram. Just try to take a look at the formula here. We are going to start our calculation after coming from break. So this is the exercise we are going to perform. So right now we will go to break and we will come back after 30 minutes. So I'm going to pause the recording. I would like to request someone to remind me to resume the record when we come back from the break, if you can. I'm going to start a timer for 30 minutes. Good to be there. Thank you, guys. See you after 30 minutes. Welcome back, everybody. So we are going to start our session after break. I'm resuming the recording. Okay. So before going to the break, we were discussing the optical power. So we are going to have an exercise. So here, as you can see, this is a typical DWDM network. And there is a city A and there is a city B, and in between these two cities there is a fiber distance of 20 kilometer. We have used boosters and preamplifiers. We have used multiplexer and demultiplexer. Both the multiplexer and demultiplexer are capable of handling 32 channels, but here we are using only 5 wavelengths, 5 channels. And the APD type sensitivity devices are used, which operates best at minus 14 dBm. Optical transponder output power is given, which is minus 3 dBm. So these are the facts. Now the question is, if we need to use an attenuator, what would be the value of those attenuators and what would be their locations to use those attenuators to maintain the optimum required power? That is the exercise, okay? Moving forward, let's find the facts we have at our hand, okay? So first, only 5 channels are used in 32 channel system. And the question is, what is the value and how many and where the attenuators should be placed to control or regulate or get optimum power for the wavelength. As you can see, the optical transponder output power is minus 3 dBm, and the optical max insertion loss is 7 dBm, 7 dB, since we're talking about loss. Again, the max insertion loss is 7 dB. There is a mistake. There should not be M. The required optical transponder receiving sensitivity is minus 14 dBm. As this is an APD type device and this type of device performs best at minus 14 dBm, so we would like to have that power for our wavelengths, right? In this example, the booster OBA, the gain is 16 dB and maximum output power is 20 dBm. For preamplifier, the gain is 14 dB and the maximum output power is 12 dBm. Distance is 20 kilometer with loss rate of 1 dB per kilometer. So in between these two cities, the fiber distance is 20 kilometer and there is 1 dB loss per kilometer in the fiber. So if we see the value 10 base log 32, that gives us 15. If we see the value 10 base log 5, that gives us value of 7. So what are these 10 base log 32? This is when the number of channel is 32. And 10 base log 5, this is when the number of channel is 5. So those are the values, 15 and 7 for these two. So these are the facts, these are the figures we have. We only need to find out where we need to put the attenuators and what value of the attenuators should we use. So attenuators are physical small module which are connected externally in the fiber path to increase loss. Now you can ask, why should we try to increase loss? Because when we design a DWDM network, It's not about high power all the time. It's about having the appropriate power all the time. So the word appropriate means in some cases it will be high, in some cases it will be low, in some cases it will be in minus figure, in some cases it will be, in all the cases, it will be a balanced state of power. You need to balance power so that you can achieve the optimum output power all the time. And to do so, you can play with the power at the input. So that is what we do in the DWDM system. Now, if we do the maths we have been talking about in this slide, as you can see, input optical power of optical mux PM equals to Pi into N, or 10 base log PM equals to 10 base log Pi plus 10 base log N. So we are talking about the input optical power. So how many channels are using? We are using only 5 channels. That means at the input, only 5 channels or wavelengths will get into the mux, right? So here we will work the number of channel as 5. So as you can see in the formula, 10 base log Pi equals 10 base PM equals 10 base log Pi plus 10 base log N. So 10 base log PM is the value where we got the value as minus 3 dB, 3 dBm, and 10 base log Pi, we got the value of minus 3 dBm, and 10 base log 5, we got the value of 7 dBm, since n equals to 5 here. So if we use the values in the formula, we get the value of 10 base log PM. So 10 base log PM gives us 4 dBm, right? That means optical multiplexer output power equals to 10 base log PM minus insertion loss. So the 10 base log PM is 4, insertion loss is minus 7. So the optical multiplexer output power will be minus 3 dBm. So this is the output for the optical multiplexer. So whatever the wavelength we are using only 5 numbers of wavelength. They are having Tx launch power of minus 3. So 10 base log Pi equals to minus 3, and only 5 lambdas are being used. So 10 base log 5 n equals to 5 gives us 7. These together gives us 4 dBm as the input power of the optical mux. So what will be the output power? So the output power will be input minus insertion loss. The input power is 4, insertion loss is 7. Altogether, it gives us minus 3 dBm as the optical multiplexer output power. Next, we see the input power of OBA. So input power of OBA equals to maximum output power minus gain. So what is the input power of OBA? Maximum output power minus gain. Here in this example, we saw that the gain of the OBA is 16 and the maximum output power is 20. So we get the input power by these two figures, which is 4 dBm, right? So if you take a look at the diagram, the connectivity in between optical multiplexer and optical booster, OBA, the multiplexer is releasing an output power of minus 3 dBm, and the booster needs an input power of 4 dBm, right? So let's see what is happening. The power of 32 channels booster equals to power of 1 channel plus 10 base log 32. if we calculate it for 32 channels, right? Because we are feeding 5 wavelengths into the multiplexer, but when the multiplexer is transmitting the signal, it is transmitting based on the fact that it has a capability of 32 channels. So when we work with the input power of the OBA, we need to consider that the number of channels are 32 to get the threshold value or get the utmost value of the calculation, right? So the power of 32 channels OBA equals to power of 1 channel OBA plus 10 base log 32. Thus, we can get the power of 1 channel OBA. So the power of 1 channel OBA gives us 4 minus 15, that is minus 11. So the power of 5 channels OBA, what should be the power of 5 channels OBA in that case? So the power of 1 channel OBA plus power of 5 channels OBA, that is, we found out the power of 1 channel OBA is minus 11 dBm. We know that 10 base log 5 is 7. Altogether, we get minus 4 dBm. So the power of 5 channel OBA should be minus 4 dBm. Now, if we go back again, the output power. So if I draw here, so let me draw here. So just okay. So guys, we have a system which is capable of supporting 32 wavelengths, right? But how many are we using? We are using 5, right? And in the beginning, we saw that the OBA and OPA, which are used, they have a gain for 16 dB and 14 dB together. And the maximum output power is 20 dB and 12 dB, right? But these OBA and OPA are designed for 32 channels, right? So we need to find out what will happen if we use 5 channels only out of this 32. This is one of the calculation. Another one, we need to find out what would be the output power here and what would be the input power here. They need to match, right? So that is another calculation. First, we are going to calculate this one. What are we doing? We are calculating this one, okay? So what are we doing? We are following the formula 10 log PM equals 10 log PI plus 10 log N. So this is the formula where we saw this P total. So P total equals P single plus 10 base number of channels. So as you can see, we are using the same formula here. P total, that is the power here, output power, total output power here is the single input power of the channel plus number of channel. So what is the number of channel here? We are using as input 5. That means this will be 10 log 5. What is the input power here? We know that TX launch power is 3 minus 3 dBm. Here at the problem statement, it was mentioned that optical transponder TX power is minus 3 dBm, right? So we know single power input is minus 3 dBm. And we know 5 number of channel 5. So 10 base log 5 becomes 7 dB. So if we do the calculation, we get the total power. Total output power becomes 4 dBm, right? So what happens if we take a look at the optical output power of the optical multiplexer, so we need to consider the insertion loss as well. To calculate the insertion loss, we need to subtract the loss from the output power. So the output power is 4, the loss is 7. Calculating these two, we get the realistic output power, which we will see at the end of the optical multiplex, is minus 3 dBm. Now we are going to calculate what is the input power of the OBA. So we take a look at the facts again, and we saw that the maximum output power is 20 and the gain is 16. But these facts are true for 32 channel, right? Are we using 32 channel? No, we're using 5. So first we are going to see what is the condition or power of the channel when there will be only one channel. To find it out, we are going to use the formula. So first we find out what is the input power. Input power equals to maximum output power minus gain, right? We saw this formula here. Here. We saw this formula here. Input power equals to output minus gain. Okay. So we have used this formula here. Input power equals to output power minus gain. So doing that, we get a value minus 4 dBm. So this is the input power of the OBA, but this power applies for 32 channels, right? So we need to find out what is the power of one single channel. So if we again use the formula, power of 32 channel equals to single power plus number of channels. That means 4 dBm equals to single power plus number of channels is 32, 10 base log 32. That means the single channel power of the OBA is minus 11 dBm. So this is for single channel. What will happen if we use for 5 number of channels? So 5 number of channel equals to single power plus 10 base log 5. That gives us minus 4 dBm, right? So this is minus 4. This is minus 3, right? So if we take a look, this is minus 3, this is minus 4. So what should be done? We need to use an attenuator here to increase a loss of 1 dB so that minus 3 becomes minus 4. So OBI input demands minus 4 dB, max output provides minus 3 dB. So we need an attenuator at input of OBA of value 1 dB. You got my point? So the input power equals to OB output minus line loss. So similarly, now we are going to calculate the pre-amplifier input power. So if we take a look, what is going to enter into the OPA, we will see the power distance or the power difference between the OBA output power and line loss will be the input power of the pre-amplifier. So we saw the OBA output power is 20, right? Where do we get it? We saw it here. So the OBA output power is 20. Okay. So we saw that the OBA output power is 20, and the line is 20 kilometer per kilometer has a loss of 1 dB. That means the line loss is also 20 dB. So if we do the math, we will see that OPA input power is 0 dB. Again, OPA input power equals to OPA output power minus OPA gain. So we saw that OPA gain is 14 dB. So we are getting 0 dB input, and we are we are also expecting gain 14 dB as per stated in the statement here. OPA gain is 14 dB and output is 12 dB, right? So putting or using those values, output 12 and gain as 14, we see that OPA input power should be -2. But here we are getting OPA input power 0 dB, right? So here it is basically 0 dB. But we need -2 to justify all the calculation. What can be done? There could be an attenuator here for introducing 2 dB loss. So we need an attenuator at input of OPA of value 2 dB. Okay. So this 12 dBm OPA output. So now after putting the 2 dB attenuator, we are having here 12 dB output. Okay. So now we are having 12 dB output for 32 channels. Again, we have to calculate what should be the output for 5 channels. Doing all the calculations just like before, we saw that for 5 channels, the output power should be 4 dBm. Okay, so the output power equals to optical equals to power of 5 channels OPA minus insertion loss. So here what is going to happen? The power of 5 channel OPA, that means we are seeing 4 dBm is entering in the OD. The insertion loss of OD, we know about it, we have been informed. That is 7 dB. So 4 minus 7 dB, that gives us -3 dB, right? For this is for 5 channel. Now output power for optical demarc 5 channel equals to output power for 1 channel plus 10 base log 5, because this is the number of channel. So the output power of optical demarcs for 1 channel is equals to -10 dBm. But APD requires -14 dBm. So we need to insert 4 dB value attenuator at input of every optical transponder, or we need 4 dB attenuator at input of the optical demarcs, which can basically save attenuator. So maybe we need 4 dB here, or we need multiple 4 dB here. So that's the calculation. So guys, does it make sense to you? Does anybody have any question? I don't see any. So I'm going to, yes, Satish, yes, please.
What will happen if we don't add attenuator?
So if you don't add attenuators, the power which was expected and required will not be achieved. That will result in having a non-balanced OSNR throughout the whole network. And if you keep continuing like this, you will see at some point, if you change gain at an amplifier for addressing any kind of fiber loss at any point, few lambdas will turn up and few lambdas will not turn up in the same path. Few lambdas might go down even because of the unevenness of the power in lambda, because of the unflatness of the power of lambda. So the
Non-linear effect?
no, this is not related to non-linearity effect. This is related to the strength of the wave, the amplitude of the wave. It should be straight at the top. So if I show you the slide here, as you can see, the wavelengths. Here, so the top is straight. See, the top is straight.
Yes.
This is called the flatness of amplitude of the lambda, the flatness of the lambda, or flatness of the power of the lambda. This is required because this is an amplifier, right? It is amplifying something. So when you input things here at the same level, now if you add something which is common to everything, it will again be amplified and become the same level, right? But when you do not adjust the power, suppose one of the channel has this, one of the channel has this, one of the channel has this. Okay, now you are sending them into an amplifier because this lambda is really weak. It needs to be boosted or amplified, but amplifier cannot selectively operate on any specific lambda. It will operate on all of them which are getting into it. So it will do the operation. Maybe you are boosting it or you are putting gain of 10 dB, right? For example, so 10 dB. So the output will be looking like this. This is the first one. This is the second one. And this is the third one. You will see the third one will be okay, but now the second one is not working because it has gone out of the threshold at the top level. You're getting what I'm trying to say, Satish?
Yes.
So that is why we need to make sure to follow the specific nominal inputs, nominal outputs, which is required by the system, by the design. We need to follow those and we need to make amends and we need to make sure that we are balancing the optical power throughout the whole network. That is the only way to keep your network smoothly running. Am I clear? Anybody has any
Yes.
question? Okay, I do not see any question. If there is no query, then I assume that you all have understood the calculation. And if this is the case, I will not discuss the next one because the next one is the second exercise and there is no solution given. This will be your homework. Go back to your place and try to calculate the same exercise with different value. Here, I'm just showing you what I have changed. I have changed the number of wavelengths which are being used, and I have changed the distance between two cities. Okay, so these two are changed. So do the math, do the calculations by yourself using this exercise, and I think things will become clearer to you. And that's the end of it. Guys, anybody has any question on this optical loss calculation topic? No, I don't see any. So I'm going to go to the next one. Card. Okay. Let's see if there is any query in the chat box. Okay, there is one. Thanks for reminding me to record. For site A, attenuation add in TX side. For site B, add in RX side. This is one direction. Yes, yes, this is being calculated at one direction. So if you try to calculate in both directions, you need to know the values for the both directions, the values of the marks, the values of the boosters, values of the amplifiers. So you need to understand you need to have those figures for both the direction to calculate the attenuation adjustment on both the sides, both the directions. Yeah, we'll say yeah. Okay, and there is no other query. I'm going to start our next presentation, which is DWDM networking design. Okay. So based on the placement of DWDM nodes and their role in the network, we can uh, segregate our node type. There is FOADM or FODM. We have already discussed that. There is RODM, ROADM. We have discussed that. There is two more, OLA or OLA and OTM. So OTM is a node which is the terminal node and which is actually adding or dropping any wavelength and delivering to client end. When we talk about OLA or OLA, it is optical line amplifier side. It doesn't add or drop any kind of wavelength. It just put amplification of the signal which is passing through the fiber via this node. So it doesn't involve any kind of modification to the wavelength, only except for the amplification of the signal strength. So that's what it does. So in OLA, no modification happens, no add, no drop, nothing. In FODAM, everything can happen, but those happening will involve physical intervention because things are fixed there. In RODAM, everything can happen. Things are automated or software controlled or remotely controlled or reconfigurable from a remote place. So that there is flexibility there. And the last one, OTM, this is just stating that this is the terminal multiplexer. This is there to drop the traffic. This is there to deliver the traffic to the client end. So if we try to understand the structure of OTM, you will see the structure will be looking like this. Here you will see what, let me use the pen again. So in OTM, you will see the OTU card, the tributary card. The OTU cards are doing the color conversion, the lambda conversion. Then there will be marks and demarks card. This is the marks and this is the demarks card. There will be optical amplifiers. There will be dispersion compensation modules. There will be fiber interfacing unit. There will be supervisory channel. So the signal comes and comes in and goes out with the fiber, and that fiber is connected to the fiber input or fiber interfacing unit. This fiber input unit or interfacing unit segregate the supervisory channel and send it to the supervisory unit, and it segregate the uh, commercial serving bandwidth or C band, and it send that C band towards the optical amplifier. Here the signals are amplified. DCM is passed here. So the dispersion is taken care, the strength is taken care, then it is demultiplexed and delivered to specific wavelength transponder unit. This transponder unit then convert the color from color to gray lambda and deliver it towards the client. At the same time, when we add the lambda, the gray lambda delivers the client traffic to the OTU, the transponder unit. The transponder unit do the color conversion from gray to color, and all the signals are connected to the multiplexer. Multiplexer multiplexes those signals, make them combine them into one signal, send it to the optical amplifier. Then from there, the signal is passed to the fiber interfacing unit and towards the next destination. And the other part for the supervisory channel from this hop to the next one is also incorporated here by this unit. So this is how the operation of OTM happens. When we talk about OLA, as I said, OLA does nothing, just amplify the signal, no modification over wavelength. So you will not find any kind of wavelength related card in this node. You only can see the cards which are necessary to receive the fiber, to transmit the sorry, you only see the cards which are necessary to receive the optical signal and to transmit the optical signal and to amplify the optical signal. So here you will see fiber interfacing units, you will see optical amplifiers, you will see DCMs, and you will see the supervisory channel unit as well for communication. As you can see, the fiber input here, you can see there is two hand of fiber input. If you go back to the OTM, it has only one hand. It is just throwing or taking in traffic from one hand, because in the topology it is the last one. It has connectivity via one hand. Okay, but if you take a look at the OLA, it has two hands. One hand is here, another hand is here. So if you go back to the topology, OLA has two hands. One hand is here, one hand is here. So OLA will have two fiber interfacing unit, and the supervisory channel will also go towards two direction. Why? Because if you look at the topology, one supervisory channel will be between OLA and this ROADM. Another supervisory channel will be between OLA and this forum. So the supervisory channel will have two directions as well. As you can see, this channel has a direction towards this side and another direction towards this side. So fiber connected from one side to the fiber interfacing unit, going into the optical amplifier and DCM, dispersion is taken care of, and amplification is taken care of. It is forwarded to the fiber interfacing unit. It combines the signal from the supervisory channel along with the received signal, which is amplified and dispersion compensated, and it forwards the signal towards the next station. This is what happens in an OLA. Next, we have FODAM, serial FODAM. So what is a serial FODAM? What is a parallel FODAM? So we have two types of FODAM, serial and parallel. So serial means that the OTU cards or the transponder unit, they are basically sending and receiving lambdas in such a way that the node is acting as it is in a serial connectivity. This is a serial connectivity, right? Right? This is a serial connectivity. So parallel connectivity means this. So if there is an OTU or transponder unit like this, where I am adding lambda, it is going this way, and some dropping lambda coming from this way. So this is kind of parallel OTU. But if we connect the OTU like this, here is one OTU, here is another OTU. This one is sending and receiving traffic via this path, and this one is also sending and receiving traffic via this path only. They don't talk to each other. That means they are doing parallel operation, though they are within the same box. right? So this is the concept of parallel and serial FOREM. So what is happening for serial FOREM? Again, it has two directions, two paths. So because of that, the supervisory channel will have two direction or two paths. The fiber inputs or interfacing units will be two in number. Then we have the east side and west side and a pass through in between them. So OTU that will add or drop lambdas or wavelengths that will go this way, or some will go this way, and there will be a pass through option as well. So that is what it is doing. But understand this is forum fixed. That means whatever you are going to do, if you take a look at this connection, these connections are actually physically attached, and they are actually hard patch using hard patch. Okay. For parallel forum, as you can see, the mux and demux units are there with the OTU option, and signal coming in from one direction entering into the optical amplifier. Then it is entering into the demultiplexer. Few are passed through, few are getting dropped to the OTU. So signal coming in from this way, getting dropped in this OTU. Again, if you take a look at this OTU, they are sending the traffic in this direction only, these two arrows. See? So they are also sending traffic from this way and receiving from this way only. Again, if you take a look at this set of transponder unit, they are also sending traffic in this direction and receiving traffic in this direction. That means these OTU are actually acting like this, and these OTU are actually acting like this. So they are working as two parallel components, though they are within the same chassis or same box. So this is the concept of parallel forum. So this is how the signal flow works for parallel forum. This is the signal flow for ROADM, WSMD4, WSMD4. So this is the, I should remove this WSMD4 name. This is basically a card name of a specific event. I'll remove this. Anyway, so that which actually mean this is a ROADM card. So wavelength switching module 4 direction. So this ROADM has 4 direction. It can support 4 direction. So again, it is placed in a topology in such a way that it has multiple hands. So ROADM will be beneficial, or ROADM will be actually efficiently used where there are more than 2 directions. Okay, here though it is shown only 2 directions, it is there to make you understand the simplicity of the operation. But at actual, ROADMs are more beneficial to those boxes or locations which has fiber availability for more than 2 directions, so that the reconfiguration can take place on the third path. So for now, let's try to understand what is happening here. So with 2 direction, as you can see, the fiber input here, same modality, it is passed through the optical amplifier. Then we have the ROADM in place. From there, we have the optical demultiplexer and the transponder unit connected. At the same time, for addition, we have transponder TX connected with the multiplexer connected with the ROADM. These two ROADMs have a pass-through connectivity in between them to pass through the rest of the lambdas. So this structure is making this site able to add or drop any lambda and pass through any lambda, doing all the tasks with reconfiguration capability remotely. So this is what it is all about. For regeneration, another type of site is there. We call it regeneration site. It's nothing but so what happens if if you recall the OLA site. In OLA site, we do not do any kind of operation, right? There is a fiber signal coming into the fiber, it's going through the optical amplifier and it's getting out. But in regenerator side, what we are doing, we are dropping the lambda or wavelength, and we are again adding the same lambda or wavelength and starting the lambda from here. So suppose we have a station A, we need to reach station Z. Now here there is a distance of maybe 100 kilometer, right? So there is a distance of 100 kilometer maybe. So what we are using optical line amplifiers to boost the signal in the path, right? Maybe 4 or 5 or 3 of them, okay? But if the scenario was like this, there is place A and the destination is place Z, and we need to travel a distance of 1,000 kilometer instead of 100 kilometer. So in that case, it is really not possible to carry the wave or carry the optical signal only with the help of amplification. So in those cases, we need to come up with intermediate places where we will break the signal and then we will regenerate the signal. We will break the signal, we will regenerate the signal. So the strength will be from here to here, from here to here, and from here to here. The strength will be calculated as the strength of 3 different lambda, but the traffic will reach from A to Z. So this process is called traffic or wavelength regeneration. So it is only needed when actually optical amplifier or boosters are failing to serve its purposes. It might be for different reasons. It might be for great amount of distance. It might be for OSNR of the path. It might be for the noise or noise increment for using multiple amplifiers. It might be for any reason, but this is the operation performed, and this is how it is performed. Signal comes, pass through the optical amplifier, then pass through the demultiplexed to drop it, and then again added as a new signal by connecting it to the multiplexer and pass through the amplifier and pass to the fiber interfacing unit towards the next direction or next node or destination. So this is what regenerator site is all about. Next, you need to have your fiber topology right at the beginning of the planning stage, because this is where it all began. You need to understand how many paths are there in each location. Like if you take a look here, we have 4 paths, right? But if you take a look here, we have only 2 paths, right? Here it has 3 paths. Here it has 3 paths, right? But here it has only 2 paths, right? So if you know about the whole fiber topology, you will be able to plan your traffic. For example, one of the traffic will be generated from here, and it is intended to go here, right? So how many paths are there? if we talk about unique path, one of the unique path is this. Another unique path is this, right? So these are the two unique paths, but we have a lot of paths, but with some overlap. So maybe so this could be another path, right? Or this could be another path, right? Or this can be another path, right? Or this can be another path. See, lots of paths, but very few unique paths. You can only use your working and protection channel as configured provision channel, and it can only be possible when you have at least two unique paths. And rest of the paths, they might get overlapped. When one of the path is down, then the system will remove the configured resource over that path, and the system will be able to reuse the overlay portion of the path along with the new portion of the path. So this is how ASON works. This is how it shows the restoration. It creates the restoration for your traffic. So this is also very crucial to have your fiber topology along with the loss from span to span, because when you do that, your vendor will ask for it during the planning phase. They will plot the same network in the simulator. The simulator will tell you how many boosters and how many amplifiers are needed to run this whole network with a very good OSNR. And at the same time, you can also add some margin. Suppose here, as you can see, 25 dB loss. So when you give this loss to your vendor, you might add plus 3 dB or plus 2 dB here, so that in future, if this fiber gets cut again and again, and after 3 or 4 years, the loss becomes 27 dB from 25 dB, you are still able to survive to run the link. So this is why it is crucial that you have some extra in your hand. And when you run ASON, when you run optical ASON especially, you should try to maintain that each span doesn't have loss more than 25 dB. If the spans have higher losses, then you will see that some wavelength is not getting up via some path, or that kind of ambiguous scenario might actually arise. Okay. OLA and OADM in strategical location. So put OLA where you do not actually need to drop your traffic, where you need to cross a great distance, and you put your OADM where you have your business, your profit, your revenue, so that you can add and drop wavelength. So when you do the power calculation, as I said, there are insertion losses, there are different types of losses. Be aware of these losses. This is an example diagram where I show different losses at different points, or different connections, different connectors at different rates. So for insertion loss of OD is 6 dB, insertion loss of OM is 8 dB, and it might vary from company vendor to vendor, card to card, and but you need to understand that there will be losses at different segments of the network. At the same time, you need to have your traffic metrics. By implementing this DWDM network, how many traffic you are anticipating to have, and those traffic should start from where and should end to where. So you should have a total list of traffic metrics with you, and you should also have the service type and protection type mentioned here. So there might be a situation where some traffic might not be included in the S1. It might be because of the investment, because of the revenue, because of the fiber topology, because of the client requirement. It might depend on different reasons, but yeah, there might be scenarios like this. So you need to have a clear understanding which traffic is passing through which condition and which traffic is passing from where to where, so that you can do the troubleshooting in case of a distress or in case of an adverse situation. Protection mechanism, there are different types of protection mechanism in DWDM. You can protect your system from OTS level towards the user network interface client node disjoint DWDM level. So as you go upwards with the protection scheme, the network availability will keep getting high. It will be more and more better as you go upwards. But at the same time, you will be introducing a lot of cost going upwards. So you have to understand what is your revenue model, how much traffic you are serving, which protection scheme is best suited for you to support your client and your business both. So that is what it is. We can give you DWDM system can give you equipment level protection, it can give you optical layer protection, it can give you electrical layer protection. The equipment level protection means having multiple boxes, multiple boards, multiple power units, and everything that is physical having multiple. The optical layer protection means whatever the optics you have is protected with the principle of OLP, optical line protection, or it can be at the line side, it can be at the client side, but whatever the side we are talking about, the methodology is basically dependent on one single criteria, which is OLP, we discussed earlier, right? Again, you can go intra-board 1+1 protection. You can use two different ports within single tributary board. You can use two different tributary boards. So those are mix and matches you can do or come up with. For electrical layer protection, you can do SNCP. You can do SNCP in ODUK level. You can do SNCP in tributary level. ODUK level means you can do SNCP towards the line side. Tributary level means you are doing SNCP towards the client side. So SNCP sub network connection protocol, it has come from the knowledge of MUX, SDH MUX, synchronous digital hierarchy. So sub-network connection protocol is a scheme where we use concurrent sending but selective receiving principle to get redundancy for the traffic. And also you can use ring. So you can provision ODUK SP ring for doing protection as well on electrical layer. I'm not going to get into the details of each and every one, but this is something you need to discuss with your vendor when you implement your own protection mechanism in your system. Future scalability. So 96 lambda is the capacity with add drop capability. So we need to find out if we need more and what will happen if you keep needing more and more and more. Optical electrical subrack separated solution, that is also a future scalability, because when you grow, you need to have more optical and electrical boxes together. So if you maintain two separate sub racks, it will be easier for you to just adding boxes in those sub racks one after another, so that you have them streamlined. 100G, 200G, 400G max ponder board. So you might want to have a board which can support different rate of transmission, so that you do not need to change your OTU board once you are going to change your capacity. The road should support 6.25 gigahertz channel spacing. We are talking about FlexiGrid. So FlexiGrid, we will discuss it later in the slide. The system should have option or capability to integrate L-band in future, and also the system should be SDN ready. Now you might ask that what is SDN? SDN is software defined network, right? And this thing basically applies to the IP layer, right? Layer 3. But in DWDM, we are working with layer 1. Then how SDN comes into picture? So the answer to that question is SDN. When we talk about SDN in DWDM, we basically mean the NMS be the controller and the DWDM boxes be the dumb boxes. The NMS will basically control all the boxes. So now you can ask what is happening now, right? Because here we saw that all the configurations are done by NMS, right? Yes, the configurations, the instructions currently goes from the NMS, but the routing protocols in different boxes runs independently. So the OSPF, TE, the GMPLS TE, the CSPF, the RSVPT, everything is running in each boxes, and they are making their own routing table to form the network and to take decision of routing a circuit or rerouting a circuit in case of ASON. But when we talk about SDN, there will be a centralized control or centralized decision maker, which is the NMS. Currently, it is a distributed ASON we are uh, experiencing or using most of the case. But when we go to higher complex network, we are basically need to turn our network into a centralized ASON, so that we can save OpEx and CapEx, and it also remains future oriented. Spares and warranty. This is something we need to be careful, because not all the vendors provide sufficient spares. Not all the vendors provide efficient warranty. So you need to make sure that you are talking with your vendor with your own requirement, whatever you need. Some might need support from local warehouse. Some might need support from foreign warehouse or overseas warehouse. Your vendor might have a local support unit, might have foreign support unit. So lots of dependencies, lots of factors are there. So make sure you have your own requirement documented and communicated with your vendor before you start your operation. Next, we have some modulation schemes. So I think, Mr. Kamal, you were talking to me regarding the single mode and multi-mode fiber. That multi-mode fiber
Yeah.
supports multiple channel and we can increase capacity. Why don't we use it? So I answered that question and I said we will discuss it later, that we use single mode fiber to achieve that. Here are the ways how we achieve that. Okay, we use single mode fiber, as you can see in the first portion of the diagram, but the signal goes with multiple planes of wave. As you can see into the fiber, the signal is entering with two waves. One is blue, another one is green. Both have the same direction towards the uh, towards the next hop or next node, but both are actually carrying traffic. So based on the modulation scheme, we have achieved this kind of scenario. So so in DWDM, we have BPSK, QPSK, 8-QAM, 16-QAM, 64-QAM, etc. So based on the modulation technique, we can basically take multiple planes and carry multiple 100 gigs within one single wave. That is how one wavelength becomes 200 gig, 400 gig, 600 gig, 800 gig. So the key component of multiplying the capacity into one single wavelength is the modulation technique of that wavelength. But it comes with some keywords, like as you can see in this table, I have plotted some differences between some popular modulation techniques used in DWDM. But as you can see here, the bandwidth efficiency, okay? So let me mark it. And I want red color. So as you can see, so for bandwidth efficiency, QPSK is low, 8-QAM is moderate, 16-QAM is high, 64-QAM is very high, right? But if you take a look at the OSNR level tolerance, QPSK requires lower OSNR. That means it can cross a long distance, but the bandwidth it can carry is not that much. For 8-QAM, it requires moderate amount of OSNR and it can carry moderate amount of bandwidth as well. For 16-QAM, it can carry pretty high amount of bandwidth, but the required OSNR level in the path is also very high. So if you are using 16-QAM for modulation of your wavelength to carry high chunk of capacity per wavelength, you need to make sure you are crossing a very short distance, or the distance you are crossing has a very, very good physical health. The fibers are well to the ideal zone of the losses. They are newly deployed. They don't have too many splice points. All those ideal things for making physical infrastructure perfect. You need to make sure that when you are using 16-QAM and 64-QAM, you are using very high and high OSNR in the path. That means your fiber infrastructure has to be top notch to carry this kind of wavelength, this modulated wavelength throughout your network. If not, you can stick to 8-QAM or QPSK. But again, if you go to QPSK, it will not be able to carry that much of traffic all at a time. So you will be losing wavelengths. So that is the keyword. So there has to be a balance between all those things. And depending on your scenario, your network infrastructure, your vendor will suggest what kind of modulation is supported by their OTU card in the fiber losses which you have in your network. So this is how this thing will come to you. I'm just sharing it to make you understand this, that how you can have a greater capacity wavelength in your network. Moving forward, as I said, the technology roadmap, QPSK, 8-QAM, 16-QAM, 64-QAM, those things. So we can have 100 gig channel, we can have 400 gig channel. So we can have multiple of big channels together, and we come up with super channel. In this super channel, multiple of wavelengths are actually placed one after another, and made a compact wavelength, and this is how a higher rate of data is carried. Again, as I was saying that with the change of modulation technique, you need to make sure that your physical layer is also maintained pretty well. Otherwise, these high level modulation will not work. Coherent network. Next, we have coherent network. So what is a coherent network? Coherent network is the modern type of network which helped us to achieve 100 gig and beyond, right? So digital signal processors electronically compensate for CD and PMD. So in coherent, we do not see the usage of DCM boxes, physical DCM boxes anymore, because the dispersion, chromatic dispersion and the polarization mode dispersion, both of those dispersions are now being taken care of by electronic of the device. So this is all about coherent. In coherent, it enables greater network flexibility, programmability by supporting different baud rates and modulation formats. So when we talk about implementing different high grade modulation technique like 8 QAM, 16 QAM, 64 QAM, we are basically talking about coherent networks, because traditional network will not be able to handle that kind of modulation technique. And it has high scalability, 100 gig to 400 gig and beyond. So as you saw, with the change of modulation, we can actually achieve higher capacity per wavelength. So what are the features? The features involve a coherent detection, advanced modulation format, polarization, multiplexing, DSP, high spectral efficiency, long distance transmission. So all those features are exclusively available for coherent network, because when we talk about coherent network, we basically highlight few things. One of the thing is modulation technique. Second thing is higher bandwidth. Third thing is digital compensation of chromatic dispersion and polarization mode dispersion. Uh, Digital signal processing to handle advanced modulation technique, high efficiency, and also you can carry this high amount of bandwidth in long haul destinations as well, if you keep your fiber infrastructure in a very good physical health. So how this is happening? It is happening by using a local oscillator in the receiver to mix with the incoming signal. So what happens in coherent detection? Coherent detection measures both amplitude and phase of the optical signals. So this is what basically happening in coherent signal. It measures both the amplitude and the phase of the optical signal. And at the receiving end, a local oscillator or laser is mixed with the incoming signal, and at the receiving end, it helps to retrieve the phase and amplitude and polarization information, and thus it can basically process bandwidth on each plane. So this is how it is all happening. Moving forward, this is a brief difference between coherent and traditional network. So as you can see, I have plotted the basic differences between these two. So this is what we just discussed. So go forward with it, and this is for your information. Channel spacing. During our discussion, somebody mentioned about extended C-band. At that time, I told that person that we will discuss it in later slide. This is the slide. as you can see here, the C-band, extended C-band, ultra extended C-band, and then L-band and extended L-band. So lots of bands are there if you run out of your wavelength while serving your client. But all these extensions, they come with a price. So you have to make sure that you are using the existing C-band with the utmost efficiency which can be maintained in a network. At the same time, you need to reconsider or you need to rethink about the revenue you are generating by investing more into the extended bands or into different bands like L bands. So whenever you are going to deploy L bands, you need to again purchase filters, amplifiers, and mux demux units which can actually understand and handle L bands. So, so you can understand using L band is again another phase of complete new investment type investment. So yeah, fixed grid. So when we talk about fixed grid, that means the baud rate of each wavelength is same. So not baud rate, the frequency of each wavelength is the same we are maintaining. So as you can see in the diagram, for 100 gigahertz, it's carrying 40 gig. Next 100 gigahertz, it's carrying 100 gig. Next 100 gigahertz, it's carrying 400 gig. Again, next 100 gigahertz or next wavelength might be different. So if you take a look, the 400 gig traffic carrying wavelengths are utilizing all the space it has. But if you take a look at the 40G and 100G wavelength, they are actually wasting spectrums there. So if you use a constant frequency grid to configure your whole network, you will be losing a lot of spectrum in this scenario or in such way. So the solution is to use flexi-grid network. The flexi-grid network means the amplifiers are now understand the grids which are flexible. The Mux Dmux units understand, the OTU units understand. So now if you take a look at the diagram, there is 1 tera, there is 4 gig lambda, there is 200 gig lambda, and each lambda is assigned a spectrum in the spectrum window as per its own necessity. As you can see, the 1 tera is needed 150 gigahertz, so it is given that. But at the same time, the 200 gig is needed 37.5 gigahertz only, and it is given that. So this is how we can basically manage spectrum with a lot of efficiency before going into more investment by exploring extended C-band, ultra extended C-band, or L-band. So how is it done? So it can be done by doing slices of the spectrum in very smaller size, like 6.25 gigahertz or 12.5 gigahertz, etc. sizes, so that you can add a small amount of window with each other and do not waste a huge chunk all at once. So this is what we call flexi grid, flexible grid. So flexible grid technology helps you to save bandwidth spectrum or wavelength spectrum and make use of this spectrum with a high efficiency. Questions, guys? Any questions so far on this one? No, I don't see any question. I'll see the chat. No, nothing on the chat. In that case, I'm going to stop this one and I'm going to start the last one. The last one is DWDM operation. we do not have much time, so I'm going to go through this one. So DWDM operation, when we talk about DWDM operation, we basically want you to understand that it is all about light, it is all about fiber, at least 90% of it. Rest of the 10% will come from different active part fault, but at least 90% of the fault you have in your DWDM system or you will have in your DWDM system is associated with either light or physical fiber. So you need to have a team like this who can basically row a boat over a river, climb an electric pole with caution and ditch the electric line and then do operation on the optical fiber. You need someone who has that kind of technical ability, that kind of dedication, that kind of courage, and that kind of motivation for job to achieve the goal. So that is very crucial. As you can see the diagram in the picture, this is from my previous organization, Fiber at Home in Bangladesh. So this is one of the uh, picture in a city where it was flooded and fiber needed to be rectified, and they were climbing an electric pole in the middle of water and doing operation on the optical fiber. Okay, this is what basically will keep your DWDM network keep going forward. That is that is me being realistic. But apart from that discussion, you also need to maintain some other things like fiber loss optimization. So you need to make sure your backbones, your connector loss, your splice loss, all those losses are kept at the most minimized level. So whenever there is a fiber cut, whenever your fiber team or field team is splicing the fiber cut, you need to make sure it didn't cross your required threshold value. If they do, then you need to reinsure or resplice or come up with a with another new price. So optical loss optimization is a very, very crucial thing in DWDM, and you have to maintain it in your day-to-day life if you are running a DWDM network. If you are in the operation team, you have to make sure that you are keeping your eye on the losses of your physical optical path so that the losses are not changed in a drastical manner. You have to make sure you're doing proper reporting on different topics from time to time, maybe once in a month, once in a week, once in every 2 days, whatever the frequency you need, you make sure that you're doing those reportings because you might not take a look at those reports each and every time, but trust me, you might need those reports when you are doing a complex troubleshooting later in the future. So keep the reports coming in and keep the reports as a log so that you can take a look at the history or the pattern of the system and understand what is wrong with this system right now during troubleshooting. Environmental hygiene is a very important, significant factor in DWDM. You have to make sure that you are using a dust-free environment, you are maintaining proper connector caps, you are putting dummies in unused card slots or interface slots, you are using patch cords with highest quality possible. So all those things you need to make sure so that your chassis can keep working. The lambda generated the lambda generator cards or the wavelength generator SFPs, they are dust free and the communication is taking place smoothly. Okay. Next, power. You have to make sure you have good redundant power capability for DWDM nodes, because if one of the DWDM node goes down, lots of wavelength may go down, and if uh, we are talking about DWDM wavelength, then actually we're talking 10 gig and beyond. Might be 100 gig, might be 200 gig, might be 400 gig. So power is a very much crucial thing in DWDM system. So if you are thinking about putting a DWDM system into a network, you have to make sure that you have taken care of the power first, and then you are proceeding forward with your DWDM plan. Temperature, this is one of the another crucial part of DWDM. So if you do not maintain the temperature properly within the threshold or recommended threshold of the active parts, they will start behaving irrationally. So maybe the WSS card will get hung, maybe the fiber interfacing card will not be forwarding the signal towards the optical amplifier. Maybe the gain will be different. Maybe the amplifier will not be working. So maybe the wavelength will be changed and distorted. The signal will be distorted. So lots of things might happen if you do not put the boxes or the active equipments in proper suggested recommended temperature. So make sure you are providing a very cool and clean temperature to your DWDM boxes. By the word clean means you have to do the cleaning regularly, because if you go back to your device and pull out the filter of the fan, you will see that the first picture, which is complete pitch black, and if you clean it, it will become something like the later one, which is ash. These two pictures are for of the same fan filter, but one is before washing, another one is after washing. So you can guess how much dirt can be accumulated by the fans which are running inside the chassis. So make sure you're cleaning these filters regularly, at least once every month, so that your fan can actually suck the cold air and keep the device cool enough to make the temperature inside the device within the recommended threshold. We have OTDR, optical time domain reflectometer. This is a great tool to find out fiber break or high bend in the optical fiber path. There are different vendors in the market. You can have one of them. With the help of this, you can basically throw a laser which can basically find out where the fiber is cut, and by following through that distance, you can find out the physical location and do the digging and find out the underground cable which needs to be rectified. So this is a very helpful and mandatory device in DWDM. In some vendors, in some cases, you do not have to have external OTDR. Nowadays, people are purchasing or buying or implementing solution which has the OTDR system integrated with the vendor's DWDM system. So you can basically do the OTDR sitting inside your NOC from the NMS by yourself. You do not need any extra men to do that. So that's a very handy feature, and that's a very required feature in case you are working with optical S1, especially optical S1. So yeah, that's OTDR. Then we have optical power meter to measure the power of optical signal at different links. We have fiber cleaning kit, which can be used to clean the tip of any fiber connector or SFP connector. So you can use it to make the environment clean for your devices. You need trained NOC and field engineer, as I was saying. So trained NOC engineers are also required because The INNOG engineers who are keeping eye on NMS, they need to understand what is the dependency of one link going down, and what is the impact of any specific link going down, if there will be any outages, if there will be any impacts on the traffic or risk involved. So they need to understand all the alarms. They need to understand the effect or impact of any low level alarm or high level alarm. So to summarize the thing, they need to be very much expert on the uh, definition on the working procedure of alarm and DWDM both, so that they can actually escalate things as per the necessity of the situation. So that would be all. I have also added a glossary of terms where I have added a lot of definitions starting alphabetically, and also added a few reference links where you can find a lot of documentation on DWDM as well. So I have some more things to share, but before that, I would request everybody to take the survey. So guys, please go to the INNOG Academy page and open the course material. There you will see that just below the time schedule, a survey link is there. So I will use a 10-minute break before 10, maybe 5 minute, maybe 5-minute break to complete the survey. Here, as you can see, if you go to the Academy page, and if you go to the event, click on the course material, you will see in the quick links, there is a survey link. You guys can see my screen, right? Yes, thank you for letting me know. So please, everybody, complete the survey, then we will say some concluding words, and we will discuss summary of today's discussion. We will talk about any question. We will discuss any feedback if you have any. So before doing that, please complete the survey first. So this is 5:23. We will start 5:30 again. For your convenience, I have shared the survey link in the Zoom chat. So everybody, please complete the survey from the link in the Zoom chat. Thank you. I really appreciate your confirmation on the Zoom chat of completing the survey. So guys, please let me know if you have completed the survey in the Zoom chat so that I can wrap up the session. Is there anyone who hasn't completed the survey? I can see we have about 44 to 45 people in the room. So please complete the survey first, then we will again start talking about today's session. Thank you. Okay, so I was looking at the chat. Somebody asked, what is OpenZR Plus? I also didn't have any idea about that. So I looked into the internet. So I think it's some initiative which can basically support higher and longer range of distance with a high rate of modulation. So this is something which is not vendor dependent, it is vendor independent, and it is also using optical FEC for time mapping and high performance. So it looks like it is something very promising to work with. So that's the answer to you, Manu. I don't know if I myself just got educated about it just now. So maybe I can talk about it later when I know about it more. But for now, that is what I understood. So yeah. Next, Rajkumar was asking how to do practice in DWDM in virtual environment. Look, for now, there are a very small amount of software which can basically support doing virtual labs on DWDM. So I'm not going to mention any name right now because most of them are paid. If there were any open version or free version, I could have suggested, but for now, I do not have any unpaid uh, virtual environment to my knowledge for DWDM. Okay, Balasa, require recorded video, mails and training. You will get the reply. So a lot of requests were sent for the recorded video. So you will get reply gradually. Can we use coherent in DWDM or it is totally? So that page coherent is basically about DWDM. So whenever we are talking about coherent, we are basically talking about DWDM because coherent involves the modulation of wavelengths like BPSK, QPSK, QAM, etc. It involves the um, digital uh, digital control of chromatic dispersion and polarization mode dispersion, which is also a part of DWDM. So whenever we are talking about coherent network, we are basically talking about DWDM network only. I hope that answers your question. Share recorded video. Kamal, you can ask for the recorded video by sending an email to training@epinic.net. The training team will facilitate that you will have the recorded video. Okay, Satish, can you give key difference in brief on OTN and DWDM? DWDM is the technology, OTN is the soft part of that technology. So DWDM is me and OTN is my emotion, my thought process, my brain activity, how I process all the information in my head. That is OTN. I hope that makes it clear, Satish, the simple analysis.
Okay, thank you.
Can we get recorded video? Again, the answer is to get the recorded version, please send an email to training@epinic.net. Can we get certificate? Yes, you can get certificate. Again, you need to send a request for your certificate to training@epinic.net. I hope that answered all of your questions. So today we have started our discussion from RODEM. We try to understand the concept of RODEM. We try to understand the concept of S1. We try to understand how the optical calculation takes place in DWDM. We did an exercise to find out the optical balance in an example network. We try to go through some planning concept in DWDM, like what is coherent network, what is OTN, what is the topological placement of different DWDM box, like OTM, like OLA, FORAM, RODAM, how the signal passes through each and every one of them. And we try to understand how the restoration work in ASON, how the protection work in optical layer. We try to understand some protection scheme. We try to understand the FlexiGrid, idea of FlexiGrid to save or to use efficient spectrum of wavelength. And at the end, we try to see what are the crucial highlights to operate on a DWDM system. So in this course, this is the first time INNOG is running this course. We really are looking forward to the feedbacks you are providing, because based on those feedbacks, we are going to modify or update or upgrade or do all kinds of addition to the course. And we will try, we cannot commit right now, but we are still trying or in phase of trying to accommodate labs along with this theoretical course. Maybe next year we will be trying more hard to get an option to do the labs with alongside with this practical course. So that's about it. That's the all we discussed today. Thank you very much, everybody, for a lot of interaction, for the questions, for the involvement, for the engagement. So I really thank everybody for joining for last 3 days and finding time in your busy schedule. I hope I delivered everything within my knowledge or experience. So if I forget to deliver anything, or if I couldn't answer you properly, or if I couldn't explain things properly, then you are most welcome to let me know. As you can see here, this is my email address, zubair.khan@epinik.net. So if you go to the event page and course material, you will find my email address. If I still fail to answer you or explain things to you, please feel free to send the queries over email. I will try to make time and get back to you after sorting out the answers. So thank you very much. And the floor is open. If anybody wants to say anything or share anything, you are most welcome to do so. You can raise your hand and then you can give your feedback. Yes, Mr. Kamo.
Sir, I just call to say thanks to you rather than raising any query, sir.
No. There is no necessity to thank me. I'm just doing my job. But I thank all of you to make me realize there are so many scope to develop this course more and more. So I will be keeping working on this course, and I will be actually doing some changes based on the questions and interactions I had with you guys during last 3 days. So I'm looking forward to that. Maybe next year I can come up with the next version of this course. So thank you very much. I would like to request all of you to turn on your camera so that I can take a screenshot and I can share it internally and keep a piece of memory for all of us.
Sir, actually, I just have one small suggestion. I feel that actually, na, we should be adding like around this niche, the new technologies of router optic networks or anything like IP or DWDM, na, which is going in the real tested trend actually, which can be added. It will be easy for useful for everyone.
I hope you have put the comment in the survey feedback, right? Thank you very much. Because if you don't document it, it will get lost. The idea will get lost. Okay. Since you have documented it, what we do after each and every session, we do a debriefing internally among ourselves. There we discuss what to pick from those feedback and what not to. So we will go through that, and definitely we will try to come up with the suggestion you are providing. Thank you. Thank you very much. Yeah. So again, requesting you guys to turn on your camera so that I can take the screenshot. Is that all? Okay. Yes, thank you very much. Yes, Mr. Firoz, you have raised your hand. Do you want to say something?
Bhai, Assalamu alaikum. I am from Felicity IDC. But can we get recording?
Yes, you can get the recording. You have to send a request email to training@epinic.net. Training team will facilitate the recording towards you. So yeah, you can.
Thank you so much, Bhai.
Thank you, everybody. Thank you very much. I'm just now shutting down the Zoom session. Thank you.